Hello, everybody. My name is Mark Williams. I'm here to talk today about power-saving mechanisms and wireless clients. I want to give a big thank you to CWNP for having me here today, giving me the opportunity to speak to you. It's a great honor. I don't have a biography slide in my presentation, so if you want to find out a little bit more about me, you can look at my presenter profile on the CWNP Wi-Fi Trek page. So I imagine that, I used to teach college for a little bit, and in college, the students are kind of like Wi-Fi clients. They're asleep half the time, right? And that's something that you don't think about too much as you're working with your clients, is some of the times they're just out. They're knocked out. So as I go through this, I just have two goals. Is that one, I hope that you learn something about wireless client power saving that you didn't know before. And two is that you don't go into power save mode at the same time. Okay. Why do we need it? So power saving is required because just listening to Wi-Fi takes a lot of energy. So in 802.11n chipsets, 802.11n and then 11AC chipsets, you have these things called low noise amplifiers. So they're connected to your antenna, and they're designed to boost the signal strength that's received over the air so it's more useful to the chipset. And a typical low noise amplifier is going to draw about 40 milliwatts while active. Now, if you take that number and you think about a 9-volt battery that you typically see in your smoke detector, that's 170 milliamp hours. And if you hooked up a low noise amplifier to a 9-volt battery, it would kill that battery dry in 17 hours. Just listening to Wi-Fi, not transmitting, just listening for frames. To save power, the LNAs can be turned off. So that's what the client power saving is essentially turning off that LNA or putting it into a bypass mode so it's not drawing as much power. So the remaining slides are a discussion about how do clients do that, and what are some of the mechanisms the clients use to save power. First off is the traffic indication map. So this is an element that's contained within beacon frames. And what it does is it lets stations know if there are frames that are ready to be received for that client. Access points will buffer unicast frames towards the clients in case they are asleep, and clients can wake up and listen to those beacons to see if they need to wake up and get that data. They're announced in the way that the DTIM works is that basically the association ID of the client is somehow communicated in that beacon. If there's no buffered frames for a client, it can go back to sleep or remain in sleep. A lot of info on this slide, but I'm trying to get through it. APs are buffering broadcasts and multicast traffic to be delivered at specific intervals. That interval is called the DTIM. It's an integer multiple of beacon frames. Clients are supposed to wake up at every DTIM interval, but do they? How many people think they wake up at every DTIM interval to see if there's broadcast or multicast? They don't. Okay, they're supposed to, but they don't always do it. Now, short DTIMs, meaning that multicast broadcast interval is every beacon, means that clients have to wake up every beacon to see if there's multicast or broadcast traffic. That means they're running through power more often. A longer DTIM means they could sleep longer, so they don't have to wake up every beacon to see if there's traffic. But longer beacons could also mean more multicast traffic is being buffered at the access point, and you can get into an overrun where the AP does not have enough buffer space to store multicast traffic. Here's a word of wisdom. Don't use a DTIM greater than 1 if you're using multicast voice applications, okay? I work for Sutter Health, a major healthcare provider in Northern California, and we use multiple applications that have voice over multicast. So nurses will get onto a mobile device, press a button, and make a call for a code blue or something, and that's multicast over the air. Those devices only have a jitter buffer of 100 milliseconds at the most. And if you have a DTIM of 3, that means you're waiting every 300 milliseconds to get audio data, and the audio is going to be unrecognizable for the users. Here's a look at a DTIM information element in a beacon. So you can see in this example, we've got a couple of things happening. One of them is the multicast true bit is set. So that means after this beacon is sent, the access point has multicast traffic it needs to send. It wants people to be awake to get that traffic. And then this one, we're also telling the client with association ID 1, wake up. It's time to wake up because I have some unicast traffic for you. The listen interval is another power saving mechanism that's communicated from the client to the access point. The listen interval is basically telling the AP how often that client is going to wake up to listen to beacons. The access point could use that information for determining a few things. It could use it to say how long I'm going to buffer frames for you, because if the AP knows that I'm only going to wake up to listen to every 20th beacon, that it needs to store those data frames for me for at least 10, 15 beacons until I wake up. It could also be used to determine timeout values for security timers, like the four-way handshake timers and EAP timers. I haven't seen a lot of evidence of that. Most of the time, when you set those values in your wireless controller or in your AP, those are what's going to take effect. It doesn't matter if a client is going to send a listen interval value of 20 beacons. It's going to want to change those keys or complete the four-way handshake within a certain amount of time. Some clients will specify a really long listen interval value, even when it's not a smart thing to do. One of the presentations earlier in the conference was about voice over wireless, or IP calling, or Wi-Fi calling. And if you take an iPhone and you configure it for Wi-Fi calling, you connect to an access point, it's going to specify a listen interval of like 30 beacons. Does it make a lot of sense for something that you want to receive a call with? That I'm going to wake up every 3 seconds or something to see if I have an incoming call? Not really, but sometimes they're just going to specify those really long listen intervals, even if you are running a real-time application on that device. Next bit is more data. So if I'm sending data to a client, one of the fields that's in that data frame is a more data bit. More data bit set to yes. You're telling the client, don't go to sleep. I'm sending you more data immediately. More data set to no. You could turn off your low noise amplifier and go back to sleep if you want to. Okay. When I put this presentation together, this is what I was going to start with. This function of power saving, power save polling. This is what most people are familiar with when we talk about power save mechanisms in clients. But as you dig deeper into it, you realize that power saving starts right at the beacon. That's where you're structuring how clients can do power saving. So I wanted to put those elements in first. This is known as legacy power save. So a client can send a null data frame to an access point, let it know that it wants to go into sleep mode. Now, the tricky thing about power save polling and these null data frames that tell the access point, I'm going to go to sleep, is the client isn't actually telling the AP that it's going to sleep. The client is telling the AP to buffer unicast frames for it. You never really know if the client's actually asleep or not, because a client could wake up its low noise receiver to listen to beacons while the AP is still buffering unicast frames for it. So when you're doing captures that show traffic between an access point and a client, you may see the QoS null data frames that are saying, I'd like to go to sleep, or I'd like to wake up now, but you actually don't know if the client's receiver is powered off. All you know is that the client is telling the access point, buffer unicast frames for me. You wake up out of a power save mode by sending a null data bit with that null data frame with that power save bit set to 0. Time to wake up. A more advanced power saving mechanism is UAPSD. This is particularly helpful in voice over IP applications. Instead of having to exchange null data frames and ACKs to go along with that, clients will automatically enter and leave power save states upon receipt of packets. So you have a voice over IP handset, you're in RTP audio stream. RTP audio streams are very predictable. They're 50 frames per second, 20 milliseconds between frames. So the client can be in a power save state, 19 milliseconds in between frames. I could be asleep. It'll wake up the receiver, it'll transmit a frame. The AP will see, oh, I got a frame from that client. That means it's awake now. I'll transmit a frame to it. And then the client goes back to sleep. So rather than using the null data frames to trigger a condition of the AP knowing to buffer frames for or not, it's just using a receipt of a data frame from the client, and it doesn't have to be a null data frame. Very useful for voice over IP. Anybody know of any conditions where this could be an issue for voice over IP applications? Where UAPSD might break some things? How about going on hold? You're on your voice client and you get put on hold. The RTP stream from your client ends. What if there's no RTP coming down from the remote end? So that could cause you an issue. Now on to a little bit more advanced topic in the spatial multiplexing power save. This is something that's used in your HT and VHT PHYs. If you have a client that has multiple receive chains, not all of them need to be active at the same time. So if you have a client with 2 receive chains, that's 80 milliwatts for power draw to power both of those receive chains. If you have more than one, you can power all of them except one off. Excuse me. You can indicate to your AP when you associate what kind of power save mode you have. You have dynamic, which is you're going to negotiate which chains are on and off while you're associated. You could have static, only one chain ever active, and then disabled. All chains remain active all the time. Okay? You determine that when you associate, and then you could change your power states while you're associated by sending an action frame. And the times that you typically see those action frames is when you dock or undock a laptop. When you're undocked and you're not on a power source, you're going to go into a dynamic power save mode. When you dock and you're connected, you'll go into a disabled where all chains are active all the time. Now here's an example of a power save association where the client is telling the access point, what mode am I going to be in? And this is a dynamic mode association. This means this client is going to put all but one of its receive chains into a sleep mode during normal operation. And then the access point is going to have to tell it to wake up both chains on receipt of data. These are the action frames that get sent. A couple of examples. One of them, the first one there is the client is telling the AP to disable disable the spatial multiplexing power save, so both chains are going to be active. So the first one would be the laptop goes onto the dock and it's connected to power. And then the second one is I'm going to go to dynamic power save mode. I undocked a laptop. I need to save some power. Makes you think about the kind of nasty things that you could do in an environment where you don't have protected management frames. You can send a frame to an AP telling a client, well, I'm going to stay in static power save mode all the time. And then that way the AP will send 2 streams to a client when only one receive chain is active. Next section is 802.11h. 11h, you might know, what's the big feature of 11h? Has to do with radar, right? Channel switch announcements. So if you get into a situation where you're detecting radar, channel switch announcements are covered under 802.11h. Two of the other features within 11h are local power constraint and transmit power control requests. So a local power constraint is more of a regulatory thing than anything else. You're specifying a power limit for your clients. So it's not intended for saving power. It's more intended just as you have to keep under this power level for regulatory reasons. And then a transmit power control request, as part of 11h, is a client can actually request from an AP how the AP hears it. And what it will do is the client sends a request at a specified data rate. The access point receives that request at a certain RSSI or DBM value. And then the access point is going to send back to the client essentially a fade margin. How many DBM are you over the amount that I require to receive your frame at that data rate? And the client could take that information and then decrease its transmit power. So if the AP received this frame for me at 12 megabit data rate, and it received it 10 dBm higher than I needed to decode that frame, the client could reduce its transmit power by 10 dBm. There's something similar in 11K as well. They just call it a link measurement request. But the elements within the link measurement request are precisely the same as they are in a TPC request. But before that, you got neighbor request and report. So as a client is roaming throughout an enterprise environment, it can ask an access point, what APs are near me and what channels are they on? With that information, the client, as it's moving, could spend less time and power scanning channels. It will only scan the channels that were returned in the neighbor report. Now, an analysis of this shows that in terms of saving you time on roaming, it only saves you a few microseconds on roaming. It doesn't do you much there, but it can save you the power, because if you get a limited channel set back in the neighbor report, that's a lot less probe requests being sent. The link measurement request does the same thing that I just talked about in a transmit power control. You could send a request to say, how well do you hear me and what's my fade margin? And the AP can report back. Neither one of these things, the link measurement request or the transmit power control request, are implemented in any client set that I've ever seen. Why do you think that is? Why do you think you would not implement a way to reduce the transmit power for a client? It was talked about briefly in one of the previous presentations about OFMDA. If you give away a client to tell it, you can reduce your transmit power, that's going to result in hidden node issues, where the client is going to say, oh, great, you can hear me really good, well, I'm going to crank down my transmit power. But that client that's connected in the opposite direction from the AP will no longer hear the client that reduced its power, and you're going to get collisions at the access point. So it's a problem. It's a solution in search of a problem, is what it is. You're not going to get, you may save power, but you're going to degrade the performance of your network. 11V can save some power too. 11V is well known for the BSS transition requests, but you have max idle, which can tell a client how long it can sleep before it has to wake up. So basically all this does is it will communicate to the client what its idle timeout value is. If you sleep for longer than this amount of time, you're going to be disconnected from the network. And another less used option within 11V is directed multicast service. In this, a client that wants to receive multicast traffic will let the access point know what groups it wants to receive traffic for, who it wants to receive them from, and some other information like UDP ports, et cetera. The access point's then going to convert that multicast traffic to unicast, downstream from the AP to the client. What does that do for you? A couple of things. Since it's now unicast traffic instead of broadcast, the access point can buffer the traffic and wait for the client to wake up to send it. APs buffer multicast traffic, but if a client is not awake at the DTIM interval, it will not wait for the client. It's going to send that traffic. APs will wait for a client to wake up to send unicast traffic. The other thing is unicast traffic could be sent at a higher data rate than multicast traffic. Multicast traffic is typically sent at the highest mandatory rate configured on your AP. Unicast traffic can be sent at all the MCS rates. Faster means less time taken, less power consumed to receive the traffic. If you have an access point and you connect some Apple clients to it and your AP supports 11V, you will see this. All the newer iOS devices support DMS. Only have 40 seconds left, so I'll wrap this up. Power saving, WNM sleep mode. A client goes into an extended sleep period, so long even that you could skip group transient key updates. WNM-Sleep mode requires TFS, which is traffic filter specification. The client communicates to the AP basically an access control list of what traffic I would find interesting enough to bother waking me up to receive. This is not implemented either, because if I'm gonna go into an extended sleep mode, I'm just gonna turn my radio off. You hit the lock button on your smartphone, 30 seconds later, your radio's turned off. You're disassociated from the network. Put it all together, here's a capture that shows a client associating to an access point. And you could see in the first couple of columns the MAC addresses. The next column is listen interval. So that's somebody that's specifying a listen interval of 14. That's in hex. So that's not 14 beacons. That's like 30 beacons or something. That's a client that really does not want to wake up very often. It specifies the association ID and the association response. And then you could see a couple of beacons there where the access point is advertising, hey, I need association ID, was that an A? I need association ID A to wake up. I have some data for you. The client sleeps through how many beacons there? 8. Finally wakes up. So clients don't always wake up when they need to wake up. They'll wake up when they feel like waking up, because battery power is more of a priority to them than anything else. Finally, a couple of slides on device considerations in the future. If you have a smartphone and you put the lock and you lock the screen, it'll usually just turn off the radio and disassociate you from the network. Tested with iOS devices and Android devices. Sometimes there's a delay, like 30 seconds or so, you'll sometimes see that client is still associated, but then after that, it's disconnected. Sleep behavior is different between locked and unlocked. So if you're active on your phone, you got an app open, the screen is lit, it will behave differently in terms of going into and out of sleep mode than it will as if the screen is locked. So I tested this with some Wi-Fi calling. Phone active, screen on. Make a call to that phone, answers immediately. The phone starts ringing. You lock the screen on the phone, you make a Wi-Fi call, it's gonna be 3 or 4 seconds before the phone actually rings because of sleep mode behaviors. And that's why I say with Wi-Fi calling, don't call us, we'll call you. That's the main thing about Wi-Fi calling, is it's, especially if you're just home user grade, residential grade equipment, it's better to have it to make a call if you need it than not. And group temporal key updates, group transient key updates, don't get sent if the AP thinks a client's asleep. So if I think you're asleep, I'm not gonna send you updates. And if you miss the timers for the updates, you're disconnected. So if sleeping through a GTK update is a bad idea, you'll get disassociated from the network. For the future, this one's already been mentioned. This is target wake-up time for 11AX. You can negotiate an extended amount of sleep period between the AP and the client. And then another standard, 802.11ba, introduces a separate radio that can be put into a device that could be used to tell the receiver of the 802.11 radio with the high power, low noise adapter to wake up. And these radios will draw microwatts on idle. So you'll have IoT devices that have 2 radios in them, an 11N radio or 11AC radio and an 11BA radio. And the signal will be sent to tell that device to wake up. Thank you for your time, anybody. Any questions? Okay. Thank you.